All right, welcome to Unit 3, Trigonometric Functions. In this video, we are going to examine trigonometric functions of any angle. So in the previous lesson, we looked at right triangles, and right triangles have acute angles, angles that are less than 90 degrees. So can we do trigonometric functions with angles that are bigger than 90 degrees? Or what about angles that are negative? What? Yeah, well, let's talk about it. So we're going to think beyond triangles, but we're still going to keep triangles in mind. So we now will extend our definition of the 6 trigonometric functions beyond triangles, so we don't have to restrict our attention to acute angles that are less than 90 degrees, or even to positive angles. So to do this, we got to get a couple things straight. First off, let's remember what an angle is. In geometry, we think of an angle as the union of two rays with a common vertex. So remember, a ray has an endpoint, and then it goes on forever and ever and ever. So we connect two rays together with the common vertex right here. And again, remember, rays go on forever and ever and ever. And that's how we think of an angle in geometry. Well, we're going to have a slightly new viewpoint here. So in trigonometry, we make a more dynamic view by thinking of an angle in terms of a rotating ray. Okay, so the beginning position of a ray is considered the initial side. So in my picture down here, that is the green part. That's the initial side, where the angle starts. And the initial side is rotated about an endpoint called the vertex in blue. And the final position of the angle is called the terminal side. So we have a terminal or initial side in green, and then we start to rotate that initial side. And whenever we decide to stop is the terminal side in red. So the measure of an angle is a number that describes the amount of rotation from the initial side to the terminal side. So there's actually 4 things going on in this picture. So we have the initial side in green, and it's rotating about a vertex in blue. And where we decide to stop that rotation is the red, terminal side. And the measure of that angle is simply a number, and that number could be degrees or radians, as we've learned. But that number that measures the angle is really about measuring the rotation of that initial side to the terminal side. But to be even more specific, in an attempt to really maintain consistency and to bring in the power of coordinate geometry, we will always draw an angle in what is called standard position. And so this is trying to be consistent. So we're still going to think of the initial side and the terminal side, but we're going to put all angles from this point forward into standard position, which actually means we're going to put these angles on an XY coordinate grid. So we're not messing around anymore. So we have our standard XY axis, and you guys all know that XY axes have XY points. So now we're always, standard position always puts the initial side on the positive x-axis, always. So all angles start on the positive x-axis. And then from there, we rotate around the vertex, which is now the origin. So the origin is always our vertex 0, 0. And then the terminal side is wherever we decide to stop that angle. So in this picture, I rotated from the green to the red terminal side, and there is my angle. I'll call it theta, or whatever I want to call it. And that represents the amount of rotation I went from the green initial to the red terminal. So all angles are now going to be measured in this way. We are not going to draw angles any other way other than in this standard position. So initial side, positive x-axis, vertex is the origin 0, 0, and the terminal side is wherever that angle stops. All right, so through this format, we could actually have both positive and negative angles. So you might be like, how could you have a negative angle? Well, you can now through the standard position. So positive angles start at the initial side and are generated by rotating in a counterclockwise direction. So this first example over here, right here, are positive angles. So positive angles start on the initial side and they go up, which would be a counterclockwise direction. Negative angles also start on the initial side. Again, all angles start at the initial side, the positive x-axis. But instead of rotating up, we rotate down, which would be a clockwise direction. So if an angle starts rotating up, it's a positive angle. If it starts rotating down, it's a negative angle. So now we're allowing angles to be positive or negative. And furthermore, we're going to allow angles to continue to rotate. So we're not going to just stop in quadrant 1. Imagine an angle that starts on the initial side, positive x-axis, and it rotates all the way over here into the second quadrant. Well, that would be a positive angle, and it's now bigger than 90 degrees. It would be an obtuse angle. So those angles are now totally okay. Or we could even continue to rotate, again, start in that positive x-axis, that's always the initial side, and rotate all the way into the third quadrant. That would work as well. That angle is going to be very big. It's going to be bigger than 180 degrees. But again, you can't have such angles in triangles, but with this standard position, you can. And let's do one more here. Let's have an angle. Again, all angles start on this positive x-axis. Let's go all the way around and then keep going all the way around more into the fourth quadrant. So that is a very, very big angle that's bigger than 360 because it went all the way around and then it kept going. The point is, now through this standard position setup, we can have angles that are positive, negative, and as big and as small as we want. All right, now let's talk about something that are called coterminal angles. So through this setup, angles can either be positive or negative, and they can rotate as many times as possible. Like I said, it can go around and around and around and around. So this allows any angles to be coterminal. Now what coterminal means is that the two angles have the same ending coterminal side. So any two angles that have the same terminal side are considered coterminal because they share a terminal side. So in this picture here, we see the red positive angle that starts on the positive x-axis where all angles start. All angles start here. And it goes up and it's stopped right here at this terminal side. But now I can also have another angle that would actually be negative that ends at that same place. That would be a coterminal angle. So we have two angles, the red one that was positive and the red one, or sorry, and the blue one that's negative, but both angles ended at the same place. Even though they're different angles, they ended at the same terminal side, hence they're called coterminal angles. So listen, angles can now be any real number from negative infinity to positive infinity because we can continue to rotate and rotate and rotate and rotate. And you know, if I said to you, how many possible coterminal angles are there to this one drawn right here? Let's just call it theta. Honestly, unlimited, because check this out. If I start at the initial side and go all the way around and around and around and around and end right there, that's a coterminal angle. It just went around multiple times. Or I could, again, start the initial side and be negative, going down, go all the way around again, and end at that positive terminal side, or end at that terminal side. That's a coterminal angle. So the point is that there are infinite amounts of coterminal angles. So let's give you a little bit more specific, concrete example here. So in green, we have a 45-degree angle. Everyone sees it right here, 45-degree angle, clearly an acute angle that ends in the first quadrant. But a coterminal angle would be the same angle that went negative 375. If you're trying to figure out how I came up with that, just take 45 degrees and subtract 360. Subtract a full circle, and you get negative 300 and, so that should be negative 315. I think there's just a typo there. Sorry, negative 315 degrees. So it's a different angle. Obviously, 45 degrees is very different than negative 315 degrees, but it really is the same angle, or excuse me, it's the same terminal side because it ends. Or I could even believe this blue angle that goes all the way around 360 degrees, and then it goes another 45 degrees to end at 405 degrees. So again, here is an example of three different angles that all have the same terminal side, hence they're coterminal. The 45-degree positive green angle, the negative 315 degrees, and then the positive that went all the way around, and then some 405 degrees. So how do you find coterminal angles? It's actually really, really simple. If you're in degrees, all you have to do is add or subtract 360. And you can do it as many times as you want. You could just keep adding 360, adding 360, adding 360, or subtracting 360, and you would continually come up with different angles that have the same terminal side. Now, if you're in radians, you would add or subtract 2 pi, because remember, a full circle in radians is 2 pi. So if you're in radians, just keep adding and adding and adding, or subtracting and subtracting 2 pi, and you would keep coming up with more coterminal angles. So let's do a couple of examples to show you how easy this is. So find one positive and one negative coterminal angle to each below. So first, you don't have to, but sometimes drawing a picture does help. So 153 degrees would be somewhere over here in quadrant 2. So it started in quadrant, started on the x-axis and went all the way over here, 153 degrees. So if I want to find a coterminal angle, all I got to do is take 153 degrees, and I'll actually show you as I'm doing this. All I got to do is take 153 degrees, add 360, and you have another angle, 513, that is the same terminal side. So 513 would be all the way around 360 degrees, plus a little bit more to get me to end at that same spot. So that'd be 513 degrees. Or I could take the 153 and I could subtract 360 degrees. This would lead me into the negative, so negative 207. So negative 207 degrees would be the angle that, again, all angles start on the positive x-axis, and then it goes negative, going in that clockwise direction, 207 degrees to stop at that same terminal side. But here's the deal. I mean, I could take that negative 207, subtract 360 again. There's another coterminal angle. Subtract 360 again. There's another coterminal angle. All right, so pi over 6. Again, same thing. Pi over 6, if you remember, is 30 degrees. So pi over 6 would be right here in quadrant 1. So again, to find coterminal angles, this time we have to add or subtract 2 pi. Now, because there's a fraction involved here, if you're trying to get nice exact answers, you guys should know that 2 pi is the same as 12 sixths, right? 12 sixths is 2 pi, 12 sixths is 2. So what I was doing is getting a common denominator. So pi over 6 plus 12 sixths would be 13 pi over 6. So 13 pi over 6 is a coterminal angle. Or I could add 12 again, and I'd get 25 pi over 6. Again, you could keep adding and adding and adding and getting more and more coterminal angles because all you're doing is going around and around the circle. Or I could subtract pi over 6 minus 12. 1 pi over 6 minus 12 pi over 6 would be negative 11 pi over 6. That would be a negative coterminal angle. Now, I hope you guys are pretty clear on how to do this by hand with common denominators. But if you're nervous, just remember, when you use your calculators, don't type in the pi. Because if you type in the pi, it's going to be irrational. So if I do 1/6, so let me go ahead. I don't know what I'm typing there. So if I take the 1/6 pi, and again, I add 2 pi, but I'm holding off on the pi. So I have 1/6 pi plus 2 pi, but I'm not typing the pi. There is the 13/6 pi. And I could add 2 again. There's the 25/6 pi. Or I could subtract 2, subtract 2, subtract 2, and there's the negative 11/6 pi. You just got to make sure to put the pi out. So again, that's coterminal angles, right? It's just 2 angles or 3 or 4 angles. It doesn't matter. There's unlimited amounts that have the same terminal side. All right, so now that we know a few things, right, this is all really helping us. So we know, combining the last couple lessons together, we know that the input to any of the 6 trig functions is an angle. And that angle could be in degrees or radians. Okay, so input is an angle. But now, through measuring angles in standard position, not necessarily triangles, in measuring angles in standard position, we realize that angles can now be anything, literally anything, negative infinity, positive infinity. There are no restrictions to what an angle could be. They could be positive, they could be negative, they could be super big, super small. 1,000 degrees is possible because all you got to do is continue to loop and loop and loop and loop around that circle. So how can we use everything we now know to apply the trig functions to any angle, not just acute angles on a right triangle? Well, it's actually fairly simple. So let's start with an angle that's in quadrant 1. So even though quadrant 1 produces acute angles, it is a good starting point. So all angles start on the positive x-axis. So let's draw this angle that goes here and stops, and we'll call that angle theta. Now, this is a ray, right? So this technically goes on forever and ever and ever. But any point, right, if I just create a point right here, there is a point. And because we're now on an xy axis, a point on the terminal side does have a coordinate x, comma, y. Now, I could choose a point here or a point further out, but I'm just choosing any point that's on that terminal side. Now, check this out, right? I told you that I was going to move on from triangles, but I'm still not going to forget about them because check this out. I could draw a triangle. All I got to do is drop this straight down to the x-axis, creating a 90 degrees. Now, look what I did, guys. I just created a triangle with that point, x comma y, as the vertex of that triangle. So check this out. Look at that triangle. So now, because I have a triangle, I have an opposite side, I have an adjacent side, and I have a hypotenuse. Isn't this amazing? Okay, now, what is that opposite side? Well, come on, let's put two and two together. According to coordinate geometry, the height of the point is the y-coordinate of the point. So the opposite side is really y. And the adjacent side is really how far right that point is, which is the x-coordinate. And what about the hypotenuse? Well, okay, a couple things here, right? First off, I'm going to call that hypotenuse essentially the radius. Because if I take this point right here and I continue to swing it around and 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 around, I would make a circle. So I'm actually connecting triangles to circles to XY axis. I mean, this is amazing. This should be mind-blowing to you. So again, how do I find that radius? Well, we have a right triangle, and we know that the leg squared plus the other leg squared equals that hypotenuse that I'm calling r squared. So there is a connection between those sides. And again, this is all because I just grabbed a random point on that terminal side, x comma y. So now let's bring in the trig, right? Sine of theta equals the opposite divided by the hypotenuse. That would be y divided by r. The y-coordinate of the point, which is how tall it is, which according to my triangle is the opposite, and divided by the hypotenuse, which I'm calling the radius of this circle if I were to rotate this point around and around and around. Cosine would be the adjacent x divided by the radius, and tangent would be the opposite side divided by the adjacent side. So you see how I drew a triangle based on this terminal side, and I grabbed just a random point. I'm just calling it x comma y to be random, and I could draw a triangle, and I, believe it or not, I actually know that the base would be the x, the adjacent side, the height would be the y, that's the opposite, and then the hypotenuse I'm calling the radius, because again, you could think about the rotation of this as the radius. All right, let's do the same thing, but with an angle that's in quadrant 2. So an angle that's in quadrant 2 would go all the way around to here and would end in quadrant 2 somewhere. Now, once again, I could draw a triangle. All I got to do is grab any point on this terminal side. It doesn't matter where you grab the point. It doesn't matter, right? You can make a small triangle or a large triangle. It doesn't matter because the ratios will all stay intact. So that point is x comma y. It's actually negative x. So I want to be very clear that there is a negative x value here. Because I'm in quadrant 2. So again, drop this straight down, make a right triangle. Look at that beautiful thing here, right? So now the height again is y. The base, it would be negative. Now I know a triangle can't have a negative length, but technically this isn't a triangle, right? I'm just creating a triangle to be able to understand the trig functions. But again, the value there would be negative because I am in quadrant 2. And then again, the radius would be the length of that hypotenuse, because if I were to swing this circle around and around and around and around and around, I'd make a circle. And that would be the radius. So again, I still have x squared plus y squared equals r squared. And now sine of the angle is going to be the opposite y divided by the radius, the hypotenuse. So again, everything I just said is true. Cosine is going to be the negative x divided by the radius. So I do have to realize that since I'm in quadrant 2, it would have a negative x value. And tangent would be the y value, that's the opposite of my angle, divided by the adjacent, that's the negative x. So again, tangent and cosine would end up being negative in this quadrant because of the quadrant I'm in. All right, let's do quadrant 3. Again, an angle would start here and go all the way around here. And again, it's a terminal side, right? I just grabbed an angle, theta. And grab any point, doesn't matter. Just grab a point, x comma y, as long as it's on that terminal side. And you could imagine swinging that point around, creating a circle if you really need to. But when you make your triangle, don't ever draw it to the y-axis. The triangle always has to be drawn to the x-axis. Okay, so there's my right triangle. Now the height or the opposite side is technically negative because it's going down. The adjacent side to my angle would be negative x. And again, that actually makes sense because in quadrant 3, your x's and y's are actually both negative if you're in quadrant 3. So once again, when I find sine of the angle, I'm doing the opposite negative y divided by the radius. Now, again, it's important that you understand radiuses are always positive because radius is a length, right? The x and y are coordinates, which based on what quadrant you're in could be positive or negative. But a radius, that's a length as you go around the circle, is always going to be positive. Cosine is the adjacent negative x divided by r, and tangent is going to be the opposite negative y divided by the adjacent negative x. Now those negatives will cancel because both x and y are negative, so when you divide them, they're both going to be positive. And let's quickly go through quadrant 4 here as well. Quadrant 4 goes all the way around. And you know what? Guess what? Even if I were to go negative and get there faster, I would still have the same answers, right? It wouldn't change. So, and we're going to talk about that here shortly. So grab a point that's on that terminal side. Make yourselves a triangle with that point. There, that triangle is. And again, be careful. This time I still have a negative y, but I have a positive x. So my adjacent side would be positive because it's going to the right. And my opposite side would be negative because it is going down. So again, same thing, guys. Sine is the opposite, negative y, over the radius r. There's the radius. Cosine is the adjacent x divided by the radius r. And tangent is the opposite divided by the adjacent. So again, even though I'm now in a circle, even though I'm now in a xy coordinate grid, I can still draw triangles. I just have to draw that triangle from my point to the x-axis. So let's actually do this with numbers now. You know, sometimes when you're dealing with x's and y's, it gets a little bit confused. Let's actually do it with solid numbers. So imagine an angle that's in standard position. Okay, I can imagine an angle that's in standard position. So I'm going to draw my axes here. And it ends in quadrant 2. So standard position, all angles start in the positive x-axis. So imagine it ends somewhere in quadrant 2. Details, you know, I don't really care. I'm not going to judge that you drew it great or not. So there's my angle theta that ended in quadrant 2. And it says the terminal side does contain the point -5, 3. -5, 3. And again, that is a point that would be in quadrant 2 because it's left 5, up 3. And again, draw your triangle. That's 3. That's the height. That's -5. That's the adjacent side. So here's that angle that created that triangle. And the radius. That's the only thing I need is the radius. And the radius, again, would be this section right here. And that would be like the hypotenuse. So how do you find it? Well, essentially, you're going to use Pythagorean's theorem. So you're going to say 3 squared plus -5 squared equals the radius squared. So that's 9 plus 25 equals r squared. 9 plus 25 is 34. So sorry, I'm running out of room. 34 equals r squared. Take the square root of both. So r is the square root of 34. Just be careful. I don't think that it's divisible by any perfect numbers, but worth trying real quick. Yeah, 34 cannot be reduced. So my radius, or my, if I'm looking at this as a triangle, my radius is the square root of 34. So now if I say, hey, what's sine of theta? Well, this should be easy. It's the opposite 3 divided by the hypotenuse, the square root of 34. What's cosine of my angle? Well, that would be the adjacent -5 divided by the hypotenuse, square root of 34, or the radius, right? And what is tangent? Well, that would be the opposite 3 divided by the adjacent -5. I mean, this is so easy. And I can even ask you about the reciprocal functions as well. So cosecant would be the r value, or the hypotenuse, divided by 3. Secant would be the r value, or the hypotenuse, divided by the adjacent. And cotangent would be the reciprocal of tangents. That would be the adjacent divided by the opposite. But it's super important now here, because we're dealing with triangles to help us understand this, but at the same time, we are in different quadrants. That's why we got to consider the fact that negatives are now possible. All right, so here is kind of everything summarized. So we can now officially find the trigonometric functions of any angle, right? So let theta be an angle in standard position. You always have to be in standard position. And let x, y be any point that's on that terminal side. So r is going to denote the distance from the point to the origin, which would be our radius or hypotenuse. And we know that because of Pythagorean's theorem, we know that x squared plus y squared equals r squared, which is essentially the distance formula, by the way, too, right? If you're trying to figure out the distance formula, that's how you'd find the distance between 2 points there. It's the radius. And x squared plus y squared equals r squared connects it. And again, if you need to draw the triangle to really help you see it. And you see that the height is the y value, the base would be the adjacent value on that x-axis, and then again, now you see the r is the radius or the hypotenuse, so you clearly see x squared plus y squared equals r squared using Pythagorean's theorem. So based on this, now we know the 6 trig functions. Again, I'm not changing what I've already taught you about opposite, adjacent, all that stuff, but sine would now be y, because that's the side that's opposite my angle, divided by the hypotenuse r. Cosine would be x divided by r. Tangent would be y divided by x, and so forth for all the other ones. This becomes very clear, very, very simple. I hope this is very easy to understand. Now, some people may say, well, wait a minute, you're talking about theta, but the triangle is drawn with this angle. Well, we're going to realize that doesn't matter. That doesn't matter, because this is what we call a reference angle. It's the angle that goes to the nearest x-axis, and whether you're talking about theta or that reference angle, you're going to get the same trig functions. All right, so let's do one more problem here, or this might be a chance where you actually try this one on your own and pause it. And I'm actually going to do this without drawing a triangle, because I don't need to anymore. I know that x equals -4. I know that y equals -7, and I'm somewhere down in quadrant 3. In quadrant 3, x's and y's are both negative, so this makes complete sense. And really, the only other number I need is r, and that's just going to be x squared, 16, plus y squared, 49, equals r squared. 16 plus 49 is 65. 65 equals r squared. Take the square root of each side. Square root of 65 equals r. Try to reduce it. I do not think 65 is divisible by any of our perfect numbers like 16, 9, or 4, or 25, or 36. So that's a good number. It's done. It can't be reduced any further. But once you have x, y, and r, guys, you're done. Now, I hope you truly understand all of this, but I hate to say it. Sometimes I tell kids, listen, even if you don't understand it, all you got to do is have a cheat sheet that tells you, hey, sine is y over r. -7 over the square root of 65. Done. Cosine is x over r. -4 over the square root of 65. Done. Tangent is y, -7, over x, -4. 2 negatives make a positive, 7/4. You're done. And then you could do cosecant. It's just the reciprocal of sine. So now we're going to take the radius divided by the y. Secant is the reciprocal of cosine. So now we're going to take the radius divided by the x value. And cotangent is the reciprocal of tangent. So we're going to take the x divided by the y. And again, that would make a positive 4/7. How easy is that? I mean, come on. It's simple. Add this right here. Add this to your cheat sheet so you understand how now we don't even have to make triangles. We really don't, even though triangles are involved in thinking of all this, because sine is still the ratio of the opposite divided by hypotenuse. But if we make that through a standard position, it's the y value, it's the r value, it's the x value. It really all connects together. So the one thing this does bring up is reference angles. So the last few examples began with a point rather than an angle. So think about that. In the last 2 examples we did, all I gave you was a point. And that point gave us so much information about the trigonomic functions that we didn't even have to find the angle. Like in the previous problem, I have no idea what theta is. All I knew is that it's an angle that ended in quadrant 3. There's billions of angles that end in quadrant 3, especially when you start to think about coterminal angles, because you could go around and around and around and around and around. So again, none of that mattered, because as long as you have the point that's on the terminal side, you know everything you need to know to find those ratios. It's really crazy. So what do we do if we are given the point, or the angle, not the point? So what if we have to work backwards? Well, all you have to do is find the reference angle. So keep in mind, a reference angle is the angle to the nearest x-axis. So let me explain this with an example. So let's find all 6 trig functions of 315 degrees. Now, 315 degrees is clearly bigger than an acute angle, but this is possible. So 315 degrees is if you get all angles start on the positive x-axis. So if you just think about this, right? Walk through it. There's 90. There's 180. There's 270. And then a little bit more takes me to 315 degrees. So there is 315 degrees drawn. Now, the reference angle would be the angle that goes to the nearest x-axis. That would be this angle, right? Because that's how I want to draw my triangle. When we draw the triangle, we draw that straight to the 90 degrees, straight to the x-axis. So this is what we call the reference angle. So how do I find that reference angle? Well, I know there's 360 total degrees in a circle. So if I take 360 degrees and subtract the 315, I get that that reference angle is 45 degrees. Now, wait a minute. You guys should know and love 45 degrees. We talked about 45 degrees being one of our special ones. So essentially, the same answers that would be true for 45 degrees are true for 315 degrees. So again, if you don't remember a 45-degree triangle, just draw it real quick. The two legs are the same value, call them A and A, and the hypotenuse is A radical 2. So if I say, hey, what is sine of 315 degrees? Because its reference angle is 45, it's going to be the same opposite, A over hypotenuse, A radical 2. A's cancel, and I get 1 divided by radical 2. It's the same thing that we've got with 45 degrees, because 315 and 45 are clearly linked together. They really are. Now, the only adjustment I have to make, this is where I have to be super careful, is because I am in quadrant 4, y's are negative in quadrant 4. So sine would be -1, because the opposite side is down. It does have a negative y. And the adjacent side would be a positive x. You got to really be careful with that. So cosine of 315 degrees, again, would be the, if you're looking at my special 45 triangle, it'd be the adjacent divided by the hypotenuse. The a's cancel, and I get 1 over radical 2. But again, I'm in quadrant 3. I'm in quadrant 4, and in quadrant 4, x's are positive, so that would stay positive. Tangent of 315 degrees would be the opposite over the adjacent. That'd be A over A, which would be 1. But because my y's are negative and my x's are positive, that would be negative. So again, I don't know what point. Like, remember, this is the opposite of what we were doing earlier. There are billions of point that ends on this terminal side. So if I just grab this point right here, x comma negative y, I don't know what that point is. I know the x is positive and the y is negative. I just don't know what that point is. And what I'm trying to get across to you is that it doesn't matter. Because no matter what, even if I were to trace all the way out here and make it a super big triangle, it's still a 45-degree triangle. So even though I'm talking about 315 degrees, since its reference angle is 45 degrees, which I know and love, I could still find all the trig functions. You just got to take sine into account. You got to know what quadrant you're in, because now that we're expanding our knowledge here, we have to understand that now we could have negative values as well based on what quadrant we end in. So be very careful with that. All right, so let's do another example. This time it's going to be one that we don't necessarily recognize, but doesn't make it impossible for us. So we want to find all 6 trig functions of 141 degrees. Now, first off, listen. There's nothing wrong with you, again, making sure you're in degree mode. There's nothing wrong with you saying, oh, okay, 141 degrees, sine 141 degrees, there's my answer, 0.629. But I want you to understand this. 141 degrees is in quadrant 2. How do I know that? Well, because, again, all angles start on the positive x-axis. There's 90. If I go to a half circle, that's 180. I'm obviously short of 180. So I'm somewhere over here at 141 degrees. Draw your triangle. I don't care how big you make the triangle, how small you make it. This is your reference angle. It's the angle that is to the closest x-axis. So I think of a half a circle. So, right, both quadrants, 1 and 2 together, are half a circle, 180 degrees. Subtract away the 141, that reference angle is 39 degrees. So again, 141 plus 39 degrees takes me to that half circle. So that's how you forgot that reference angle. So again, sine of 141 degrees would be the same as sine of 39 degrees. They're reference angles. So again, I don't know that. That's not one of my special angles. That's why I'm going to go to my calculator. It's 0.629. 0.629. It's positive. I'm in quadrant 2. In quadrant 2, y's are positive. Now check this out. Cosine of 141. That's going to be the x value divided by the radius. But I don't know what the x value is. I don't know what the radius is. Doesn't matter. You have a calculator. Cosine of 141 degrees, negative 0.777. again, the last problem was 45 degrees, which I know and love, which is why I was able to find exact values. Here I can't because it's just not one of the values I love. And that's okay. That's okay. But I want to show you something else about reference angles. Remember, I told you that 39 degrees and 141 are clearly linked. Check this out. Cosine of 39 degrees. Oh my gosh, 0.777. But why is the 141 negative? Because I'm in quadrant 2. So that's why the quadrant you're in matters tremendously. So the reference angle, 39 degrees, is going to give you the same value as the 141. Cosine of 141, cosine of 39 degrees, both 0.777. But again, you really need to focus on, hey, I'm in quadrant 2. In quadrant 2, x's are negative. That's the adjacent side. Hence, that's why cosine needs to be negative. And then again, tangent as well. Tangent of 141 is going to be the negative 0.8097, or actually I'd round to 0.81. And again, check this out. Tangent of 39 degrees. Look at this. Look at this. The same value. But be careful, because I'm in quadrant 2, y's are positive, x's are negative. When you divide y divided by x, you are going to get a negative number. So hopefully this is making sense and sinking in. Let's do one more example. All right. Use the given information to find the remaining trigonometric functions of the angle theta. All right, so I have taught you in this video that sine of theta is now known as y over r. That means y equals 3 and r equals 7. Okay, how easy is that? That's so simple. Now you might be like, well, wait a minute, I thought you told us that it's opposite over hypotenuse. I did. But when you draw the triangle, the y value is the opposite side. The r is the radius, which is the hypotenuse. So I'm still telling you the same thing. We're just looking at it through a different perspective. Now, what about x? How do I find x? Okay, well, x squared plus y squared equals r squared. X is the adjacent, y is the opposite, r is the hypotenuse. So now I just got to fill in the blanks. X squared plus 9, 3 squared is 9, equals 49. 7 squared, 49. X squared equals 40 when you subtract the 9. Square root. Now, let's see here. 40 is 4 times 10, so that would be 2 radical 10. Always make sure you clean up square roots. All right, so now that I found that x, but wait a minute, I got to be super careful. Remember, because I'm now expanding my perspective, what quadrant am I in? What quadrant you're in clearly matters. Now, r is a length, it's a radius, so it's always positive. Y is clearly positive 3. So that means I am either in quadrant 2 or quadrant 1, because again, y is clearly a positive 3. But just remember, when you solve a square, you have to say, well, it could be positive or it could be negative. And that's what I need to figure out. Now, how do I figure that out? Well, look at this extra information. I didn't tell you what tangent was, but I basically was finding a kind of a tricky way to tell you that tangent's negative. Tangent being less than 0 means tangent's negative. So if tangent's negative, and remember, tangent is y divided by x. So I already know that y is 3. And I just found out that x is 2 radical 10, but because I'm telling you that tangent's negative means that the x has to be negative. Why? Because again, I can't change y. Y is clearly given to me as positive 3, so I cannot make it negative. So the only other option is that x is negative, which means I am over here in quadrant 2. I have to be in quadrant 2 because in quadrant 2, sine is positive. That means the y is positive. And tangent is less than 0, which means it's negative. All right, so now that I have all of these numbers, now that I have x, y, and r, I can find all 6 trig functions. So let's see here. Cosine of theta is going to be x, negative 2 radical 10, divided by 7. Tangent, I kind of already found, is going to be y divided by x. And let's see here. Let's do cosecant. Cosecant is the reciprocal of sine. So since I know sine is 3/7, I'm just going to do 7/3. That's r divided by y. Secant is going to be r over x. So don't forget the negative there. It's number 1 error a lot of kids make. And then finally, cotangent is going to be the reciprocal of tangent, which again is x, negative 2 radical 10 over y, which is 3. So I'm not, in this video, all I'm trying to get across to you is we're looking at triangles with a new perspective. We're looking at them on a unit circle, on a circle that is centered at 0, 0. And through this perspective, we can now talk about angles in standard position. That means they always start on the x-axis, positive, and they go around in either direction, positive or negative. And wherever you decide to stop, wherever the terminal side of the angle is, grab any point and create a triangle. And through that triangle, you can find sine, cosine, tangent. Because all you need to understand is that ratio of opposite to hypotenuse, adjacent to hypotenuse, opposite over adjacent. And even though I'm now calling them x, y, and r, they still represent the same thing. The opposite side is y, the adjacent side is x, and the hypotenuse is the r. So as long as you get through all that, this should make sense. The only really new thing you got to be very careful of here is that you can now have negative values because we're not trapped in a triangle. So negative values are possible, and to figure that out, you really need to know what quadrant you're in. That way you know who's negative and who's positive. But I will say this one more time, r is always positive because it's a radius. Radius is a measurement, it's a length, always going to be positive. All right, so hopefully you picked up everything in here. Be ready to ask questions if you need to, but I hope all this is sinking in and making sense.